Thank you all for joining our presentation. Before starting, I would like to mention that, again, what Jan said before, that this work is hugely based on the bachelor thesis of our students, Rino Kingston and Odin Ingvar, or previous students who did a bachelor thesis about this. So, yeah, huge credit goes to them. To start. Come on. Yeah, to start off, I would like to mention that some of you may know that NVE has identified a lot of regions for wind farm projecting along the Norwegian coast, and one of them being Vestavind F, here marked in red. And they did some calculations and some estimations as on how much energy such a farm put in this specific site could produce. For that, they used the ERA5 area analysis wind data set, which is quite coarse when it comes to very fine computations or something like this. They also used the IEA 15 megawatt reference turbine, and which is one choice to make. It's one turbine class which is upcoming, going to be used for projects to come. And they estimate from their calculations that there will be 70.5% of losses due to wakes and downtime, such as maintenance, by default. Overall, they estimate the capacity factor to be 50.1%, which is quite good for an offshore wind farm. We decided to calculate it ourselves using our methods, our in-house code, and see what we got, and then compare. We found some interesting results there. So I'm going to walk you through briefly through the input wind data we used. It's a little bit different from the one NVE used. Then talk about the wind turbine models and the farm layout we decided to go with. And finally, I'll give you a short introduction into our in-house code, Quinn. So the NURA 3 dataset is a reformulated dataset covering a large area of the northern sea, as we see here. And its temporal resolution is 1 hour, and the spatial resolution is 3 kilometers. So it is quite fine. And this small red square there is this area of interest, where we have the Vestavind F site and the Utsira Nur west site inside there, being a part of the whole projecting area of Vestavind F, just a little bit front of Haugesund. That being said, the turbines we decided to put in this Utsira Nur area are the 3 reference turbines, and the NRL 5 megawatt turbine, the IEA 10 megawatt, and IEA 15 megawatt, which are all respective reference turbine, not real turbines, but turbines used within research, and they are representative for their turbine class. They obviously have different rotor diameters, but they have different cut-in and more or less the same cut-in and cut-out speeds, so the same window of operation of wind speeds. And one thing I would like to mention here is, for those who are a bit more familiar with wind turbines, is that the rated speed of those turbines is slightly different. And this will show in the results later, so keep that in mind. We'll come back to that later. Now, if we put those 3 quite different size turbines into the same field, we'll get 3 different layouts here. And now you might ask, okay, we have this, it's the same basically window, the same scaling of wind farm. And you might ask, why are we not using this full field? So, for example, the IEA 15 megawatt version has this big white spot on top right. And this is because we decided to fix the total capacity and make a comparable study of 3 wind farms which have the total capacity of 750 megawatt. and also have comparable spacing between turbines to have a better comparability. Such an approach gives us, of course, a different amount of turbines also, which we picked, and a different total area covered. The capacity density also varies a little bit, but they are all within the scope of current wind farms, which are built at the Baltic and Northern Sea, at the Danish and German coast. Yeah. So now as for the methodology, we're using a steady state model. So it's low fidelity engineering models. We take in the ambient data from NURA 3 and the turbine data we get from our reference research articles, and put them into our model and get the wind speed and turbulence in the wake region of a turbine. For those interested, we use the Ishihara model. Then we correct for wake meandering. This is this lingering motion of wakes occurring through the interaction of the wake region with large atmospheric eddies. And then finally introduce some the wake mixing or through superposition, where we use the song model just to obtain the full wake of the wind farm and within the wind farm, which is the result, right? And as you can see here, this is just an example, of course, but here we have one direction which hits those exemplary 9 turbines with one wind speed. We are in steady state. But if we want to have an AEP, we need to take care of all kinds of possible wind directions and wind speeds where the windrows comes in. And this is something where it gets interesting, because here we need to look at the wind statistics at Vestavind F, and here I would like to hand over to Jan.
Yeah, so when we present the results, we will shortly talk about the wind statistics, where we did an evaluation of the wind data for 11 full years. Then we will look at the annual energy production and the associated wake losses that we calculated with our engineering model Quinn. And then we will discuss a little bit what is the influence of below rated and above rated wind speeds on those wake losses actually, and discuss a little bit more how actually our results correlate and what could have potentially influenced those results. When we look at the wind statistics at Vestavind F or Utsira Nord, we took those NURA 3 data and analyzed them for 11 full years from 2012 to 2022, and we found a nice Weibull distribution, which looks like that, and also windrows, which shows that we have predominantly winds from the southeast or also northwest dominated. But what is more interesting is that we looked into those data and analyzed them year by year for every of those 11 years, and found a quite large variation in both the wind speed distribution and also the directional distribution, which is reflected in those windroses. So, for example, in 2012, we see predominantly winds from northwest. Whereas in 2015, we see a completely different picture where we have winds from a wide sector in the southwest dominating the windrows. In 2018, there is a certain shift to winds from the southeast region, which is also different. So altogether, those windroses result in the windrows above, but we need to mention that there is a strong variability from year to year. And this variability also reflects in the annual power production that we see. So the 3 colors here represent the 3 different wind turbine types that we assembled in these 750 megawatt farms. And because of different reasons, which we will go into later, the 10 megawatt wind farm has the highest annual energy production here. But what we do see is that there's a large variation in those productions. For example, in 2015, we have 4.17 terawatt hours produced, whereas in 2021 we only have 3.54 terawatt hours produced. So that's a quite significant difference. And that difference can be directly correlated to actually the average wind speed for the different years. So we see that we have a quite high wind speed in 2015 and a quite low wind speed in 2021, which is directly influencing the annual power production. So that is not surprising. But what we also did then, and what was more interesting for us, is how does that influence the wake losses that we calculated with our engineering code Quinn. So what we did see here is that we have actually quite low wake losses in the years where we have high production. For example, in 2014 and 2015, the wake losses are in a region between 0 and 1%. For example, for 2015, we calculated only 0.5% of wake losses, whereas in 2021, where we have high production, we have wake losses that are 15.6%, and which is a little bit corresponding to the estimate that also NVE used there. So we were wondering why there is this large variation, and we were looking into how this could be influenced by the actual rated wind speeds of the different turbine types. And also we looked into how many hours per year are actually we have above rated and below rated operation of those wind turbines. So what we did see that again in those years of high production, we have also a quite high percentage of above rated operation. For example, in 2014, we had 44% of all the 8,760 hours a year, we had 44% of them where we had above rated operation. Whereas in 2021, we only had 35% of above rated operation. And this might seem not so big difference in numbers, but actually we saw that it had quite some effect on those production hours. So in order to analyze this in a little more detail, we just picked out an example now of two turbines that are in line. So we just look at one wind direction where the wind hits the first turbine. They are separated 9.35 diameters, and we have a reduced wake velocity, which is hitting the second turbine. So also for simplifying this, we analyzed a period of 4 days of wind. So that is 96 or what it is, 90 something hours. And what we did see here is that the velocity, that is the thick blue line, is hitting the first turbine. So that's just coming from the wind data. Then with our wake model, the ACR wake model, we calculated the reduced wind speed that the second turbine sees. And of course, that one is a little lower. In addition, we also see that we have 3 different regions of the power curve here, where we have rated wind speeds of 11 meters per second, where we have rated operation, and we have a cut-in wind speed, which is at 3 meters per second, where actually the wind turbines start to produce. So the red regions here are where we don't have any production because the wind is just too low to produce anything. As soon as we're above those 10 meters per second, we actually have the rated production of 10 megawatts in this case. So the power, if we look at the power now at the corresponding hours, we see that the production is fixed as soon as we have above rated operation, but it has a strong variation as soon as we have below rated variation. So the power curves for those 2 turbines in a row, they're basically the same. But we do see that the second turbine is influenced, or the production of the second turbine is influenced a lot as soon as we have below rated operation, where in regions of above rated operation, it is not influenced at all because it also sees the full wind. There's a couple of details that are interesting. So if we're just above rated for the first turbine, like in this region here, there can be a gap in production for the second turbine because the second turbine is just below rated then and will be influenced by the power production here. So, but still, we found the measure of quantifying the number or the percentage of above rated hours of operation quite useful here. So what we found is that there is a correlation, and of course, as the more above rated hours we have per year, the more annual energy production we found that we have. That number is a little higher for the 10 megawatt turbine than for the 5 megawatt and also the 15 megawatt turbine. So what we think here, what happened, and now first of all, also the wake losses that we also calculated, again, they have an inverse relation to the above rated operation. So we see a little bit of spreading here, but if we put the linear regression through those, we find those correlations, and we think they are quite significant, that we have at least an inverse relation here. Why are those different for the three different turbine types? That's a good question, which we try to find out a little bit. So first of all, it's the above rated limit, and this was a little bit different for the three turbines. The 5 megawatt turbine had a rated wind speed of 11.4 meters per second. 10 megawatt turbine had a rated wind speed of 11 meters per second, and the newest of those, the 15 megawatt reference turbine, had a rated wind speed of only 10.6 meters per second. So those 0.4 meters per second can make a difference in how many how many hours of above rated operations we actually have. Also, we have different values of rated thrust for those three different turbine models. And those values, they are in between 0.8 and 1.05, if I remember correctly, for the three different turbines. And the higher thrust we have, the higher wake effects we also have. So in some cases, those two effects of the thrust itself, but also the limit where the thrust is actually rated, they're opposing each other. And this is, for example, why we have very similar correlation for the 15 megawatt and the 5 megawatt turbine here. The 10 megawatt turbine has a more advantageous correlation here because it has a kind of low rated wind speed and an intermediate thrust coefficient here. Okay, to come to some conclusions in this presentation, we found that our wake losses had a very strong variation between only 0.5% and above 15%. And we found those inverse correlation of wind speeds with of the wake losses with wind speeds and also the power production. The main influence factors that we identified is actually which turbines were picked and what are the limits of rated wind speeds and also their thrust coefficient. So those are the two factors that we identified as the main contributors for those results. And what we also can say is that the estimate of 17.5% losses from NVE are conservative, but also realistic. Our calculations showed lower wake losses, but again, there's a strong variation to that. Last but not least, we will have to mention that it is crucial to analyze several years or even decades of wind data when calculating the wake losses, because there seems to be a very strong dependency of those wake losses from the input wind data. Okay, I think that's it for our presentation for now, and we hope that you have some questions and some